Good morning, ladies and gentlemen. Today we're going to learn about momentum and how the center of mass for a system is affected by momentum. All right, to start things off, we're going to take a look at this Phet simulation. Here I have a ball of mass 0.5 kilograms, which is in red, and a green ball with a mass of 0.5 kilograms. And I gave the red ball just a tiny little bit of velocity. Now, if I were to click on this little button here, this is center of mass, we can see that the center of mass is represented with an X right there. Okay, so this is a completely theoretical situation, so no energy will be lost. And if I push play, we can see how the center of mass moves as the red ball moves. So we'll try that again. So when I push play, because the red ball has a velocity, it will move to the right, and you can notice that the center of mass will also move to the right. Okay, so at this point you might be asking yourself, what is the center of mass? So to state, the center of mass for a system is if you were to take all of the mass of both objects in the system, if it's just one object, the center of mass will be for that one object. But if there's multiple objects, like we see in this scenario, the center of mass will be the average location of all of the mass particles. And so the average location of mass 1 and mass 2 is right in between. Okay, and that is if the two masses have the same size, or the same mass, or the two objects have the same mass. But if we were to increase the mass of the red ball, that means that the average positioning of the masses will be more towards the red ball, and I'll show you that here. So if I increase it, notice how the center of mass moves to the left. And that's because the average location for the mass of the system is more towards the left. Okay? And if I were to push play, the center of mass will also move towards the right as well. Look at that. All right. Now, let's take a look at the system when the center of mass is right in between, because the two objects are identical to each other. Okay. If I were to push play, the center of mass moves because the average location of the mass is also shifting. So for conservation of energy and for the conservation of momentum, this is very important. We say that the conservation of momentum for a system, or aka the center of mass, is always conserved. So if the center of mass has a certain momentum before and after the collision, it will always have the same momentum. So if we were to restart this, visually, if you can see how fast the X is moving, right before the collision, then again, if you can see how fast the X is moving before the collision, after the collision, the X should move with the same velocity, okay, because it has a conserved momentum, because the X represents the center of mass, M, and the X is moving, V. So let's do that again. Would you look at that? It moves with the same velocity. Okay? All right. Now, this holds true if we were to, let's say, increase the mass of the green sphere just a tiny little bit. The X moves a little bit slower, but even after the collision, the center of mass still moves. Now, you might notice something very interesting here. The red ball, we'll make it a tad bit lighter. The red ball, after the collision, because it's an elastic collision, it bounces off and it goes to the left. Even though the red ball bounces off and moves to the left, the X continues to move with the same momentum. Okay, and that's very important. Now, we've done many problems where we could figure out the before velocity and the after velocity, but now we have to start thinking about this in terms of the center of mass. Okay, before the collision, the center of mass had a certain momentum, and after the collision, the center of mass must have the same kind of a momentum. Right? So that's for elastic collisions. Let's see what the situation is like for an inelastic collision. All right, we'll make it so that they have the same mass. Okay, are you ready? Make your predictions now. How do you think the center of mass will move after the two spheres collide in an inelastic collision? Now, would you look at that? The center of mass has the same momentum. It never changed. So in case you don't believe me, let's see that again. The X is moving with a certain velocity, and even after the collision, the X is still moving with the same velocity, because the conservation of momentum is always conserved. The momentum for the center of mass before the collision has to equal to the momentum of the system after the collision. Okay, and let's see if this holds true. If we make, let's make the red one more massive. It still holds true. Okay. Now, if we take a look at this, this one's different from what we saw before when the two masses are the same. In this situation, mass 1 or the red ball is a lot more massive, which means the center of mass, the average location of all the masses, is going to be closer to mass 1. Oh, look, a fox. All right. Well, I hope you learned a thing or two about center of mass. Please review this video and take down a couple of notes. I've also included a link to the simulation so that you can play around with it yourself. And I'll see you later. Bye.